Hi, everyone. So this is the third module for the Bc32 Short Communications assignment. As you can see, this module is about study design. So in module 2, you derived a good research question, and you subsequently wrote the introduction to your first short communication, and that introduction was very much centered around that good research question that you had derived. What we're going to talk about here in this module is, now that you have a good research question, how can you design a good study that will allow you to come up with the answer to that question? So where I want to begin is by telling you that in general, there are two types of scientific studies. And I'm going to introduce you to these two different types of scientific studies in the context of one of the research questions that I derived in Module 2. So you might remember that I had come up with this question in Module 2. Does vitamin D intake affect testosterone levels in women? So we have a good research question, right? It was novel, it was relevant. Now we are turning our attention to how do we design a study that will allow us to answer this question. And so as I mentioned, there are two types of studies in general that scientists use to try and answer research questions. And the first of these is called an observational study. So for an observational study, as it says, you are going to measure the value of some parameter, or perhaps multiple parameters, in a naturally occurring population. So you're basically just going out and finding, people that you can make measurements of some parameter or some parameters within that naturally occurring population. So let me give you an example of how we could design an observational study to answer my question about vitamin D intake and testosterone levels in women. Here's what we could do. We could recruit 10 women. We could have them complete a food survey, and we could use that food survey then to determine how much vitamin D they consume on a daily basis. We could then draw a blood sample from those women to assess their testosterone levels. And then we could do a correlational analysis to see whether the naturally occurring variation in the vitamin D intake of these women is correlated with the naturally occurring variation in the testosterone levels in these women. And of course, if they are, or even if they aren't, we'll now have the answer to our question. Right? So the key thing to an observational study is you're basically just measuring the naturally occurring variation in the value of the parameters that are related to your question and seeing whether or not there is correlation between those parameters. So that's an observational study. The other kind of study that we could do to answer this question is something called an experimental study. And so for an experimental study, you are going to manipulate the value of some parameter. So this is very different now because you're actually intervening in the lives of these individuals in order to actually manipulate some value, some parameter within their body. But as it mentions here, you're only doing that for some of the individuals. You're going to leave the other individuals in the study being unmanipulated, and then you're going to see how your manipulation affects the value of some other parameter or parameters. Okay? So the big difference here is in observational studies, you're taking advantage of the naturally occurring variation that occurs within populations, and in the experimental study, you're manipulating some value within some members of the population, but not all. And so again, because you're doing this in some but not all, the manipulation, with an experimental study, you inherently have what we call treatment groups. These are the individuals that belong to the manipulated population, okay? And then you have control groups. And these are the individuals that have not been manipulated. And as it mentions here, you could have multiple treatment groups, but generally speaking, you'll have a single control group that you have not manipulated in any way. So let's think about this experimental study in the context of our particular research question about vitamin D and testosterone in women. So here's how we could do an experimental study. We could recruit 10 women. We could give 5 women vitamin D supplements. The other 5 women would not get those supplements. So now we've established our treatment and control groups. We would eventually take blood samples to assess testosterone levels in these women, and we would ask the question, is the level of testosterone different between those women who had their vitamin D levels manipulated, so our treatment group, and those women who did not have their vitamin D levels manipulated, so our control group. Okay, so hopefully what you can see here is the big difference between these two types of studies, right? Again, in observational studies, we're just looking at the natural variation, in this case in vitamin D and testosterone, and asking whether there seems to be any correlation naturally occurring. But in the case of the experimental study, we are conducting an experiment, really, right? We are manipulating the vitamin D levels in some of these women to see whether that manipulation has any effect on their testosterone levels. Now, one of the things that you have to think about in the context of the short communications assignment that you're doing as part of this course is you do have to think about whether HumMod is appropriate for an observational and or an experimental study, right? So I have these two different approaches I could take to try and answer the research question I came up with, but in part of determining which of these two types of studies I might actually utilize, I do have to think about what HumMod can and cannot do. So I actually did a little exploring with HumMod in my case, and I found that the vitamin D intake, there's no natural variation on HumMod in vitamin D intake. I can control the vitamin D intake of my patients, but it doesn't seem to vary in a naturally occurring way. And so because of that, I don't think I can do an observational study, at least not with respect to vitamin D and testosterone, using HumMod. So I know I can do the experimental study because, as I said, I can manipulate the daily intake of vitamin D. I know that I can monitor the level of testosterone in the blood, so I can definitely do an experimental study. So again, sometimes HumMod will be able to do observational studies if you have parameters that you're looking at in your study that are not fixed in HumMod. But for my particular case, a little exploration told me that I cannot do an observational study. I'm going to have to do the experimental study, and so that's what I decided to do. Now, what I want to talk about next is, okay, we have these two different kinds of studies, but when we design a study, whether it's observational or experimental, we want to make sure that we have a good study. And what is a good study? Well, I'm going to borrow the words from a book here by Childs et al., which was just published last year. This book says that the main principle of study design is to extract data from a system in such a way that differences or variation in the data can be unambiguously attributed to the particular process we are investigating. Now, that is perhaps a bit wordy, but the reason I pulled this quote is because of the bolded words here, unambiguously attributed. I would say that this is really what you're striving for anytime you design a study in science. You want to design a study in a way where there is as little ambiguity as possible in terms of how the results of that study will eventually be interpreted, right? So in my case, when we're talking about vitamin D and we're talking about testosterone, we want to know for sure that any differences we're seeing in testosterone levels in these women can be attributed to changes in vitamin D. We don't want there to be ambiguity where there could be other factors that are possibly interacting with the system that we're studying, the women that we're studying, because if there's ambiguity at all, then people will start to question our results. And we don't want that. We want our results to be unambiguous. So that is the key word to keep in your mind. You want to design a study where the results of that study will be as unambiguous as possible. And so let's come back to my research question about vitamin D and testosterone in women. And let's even come back to these two different experiments that we have designed to answer this question. And now let's think about these experimental designs, these study designs. Let's think about these study designs through the lens of Childs' statement that we want to be as unambiguous as possible. So let's start with the observational study, and let's think about where could possible ambiguity arise in this observational study. Well, one place where I think ambiguity could arise is with respect to the food surveys that we are using to assess the vitamin D intake of these women. Let's imagine that we have designed our experiment in the following way. Let's imagine that we are going to have these 10 women come into our research laboratory. We're going to give them a little journal, and we're going to tell them, write down everything that you ate over the past 24, 48, 72 hours, something like that. And they're going to write down all the foods they ate, and we're going to use that to determine their vitamin D intake over the previous 24 to 72 hours. And then we're going to draw a blood sample from these women and measure testosterone, and we're going to see if there's a correlation between vitamin D intake and testosterone. Well, where could there be ambiguity in that design? Well, one of the places where ambiguity might arise is the fact that these women may not remember what they had eaten over the past 24 to 72 hours. I mean, if I said to you right now, make a list of everything you ate in the last 3 days, do you think you could do it without missing something, missing a meal, maybe missing a snack that you had? I don't think I could do it. I sort of remember what I had for dinner last night. I'm kind of remembering what I had for breakfast, but if I have to go back beyond a day, I'm not 100% sure I'm going to remember. So a better study design might be to have these women come to the research laboratory, give them a journal, and tell them, okay, we want you to go home and we want you to write down everything you eat for the next 24 to 72 hours. And then you're going to come back to the research laboratory, give us the journal, we'll draw a blood sample, and we'll measure your testosterone levels. So now, because the women have the journal in advance, they're going to be able to write down things as they eat them. They are not going to miss or be as likely to miss something that they consumed. So now I get a much more accurate measure of their vitamin D to correlate with their testosterone levels, and I've reduced some measure of ambiguity in my study design. Another thing we have to think about here, of course, with observational studies in particular, is we're going to, even if we can accurately measure vitamin D intake and accurately measure testosterone levels in the blood, we then correlate these two things to see if there is any kind of correlation between them. But there are, of course, two ambiguities that arise just in correlation in general. The first, of course, is directionality, by which I mean we don't actually know, how exactly are testosterone and vitamin D related. So let's say there was a positive correlation between vitamin D and testosterone in my observational study. I don't know whether that's because women who consume more vitamin D on a daily basis then produce more testosterone as a result, or whether women who have higher testosterone levels are more prone to consuming vitamin D-rich foods. I don't know the directionality of that relationship. So again, there's inherently ambiguity in this study design. Also, we have the potential for autocorrelation, which means that perhaps vitamin D and testosterone are showing a positive correlation in my study, not because there's actually any relationship between them, but because there's a potential third variable that's elevating both vitamin D and testosterone. And so that third variable, I'm not seeing it in my observational study, but it's there, and it's causing high testosterone levels and high vitamin D levels. And so I end up seeing this vitamin D testosterone correlation, even though those two parameters perhaps have nothing to do with one another. Perhaps they're just both related to a common third parameter that I've not measured. So again, there's ambiguity inherent really in observational studies in general because of our inability to know about directionality and autocorrelation when we do observational studies. Of course, this is the reason why most people who do an observational study will often use the results of that study as the basis for a subsequent experimental study. So for example, let's say I did my observational study and it turns out there was a positive correlation between vitamin D and testosterone in women. In that case, again, wanting to eliminate the ambiguity of how those results are interpreted, I might then follow up with the experimental study I've described here. And that experimental study, if it shows that yes, testosterone is higher in women given vitamin D, then now I have experimental support that vitamin D is influencing testosterone, and it correlates or goes hand in hand, or complements is the word I want. It complements my observational data. So that's one thing we can appreciate, is that observational and experimental studies can be very complementary to one another. And oftentimes people will do an observational study first to see if there is any kind of relationship between two parameters. And if there is, then they might follow up with an experimental study. Because of course, if I had done the observational study and it turned out there was no correlation between vitamin D and testosterone, then perhaps there isn't a need for me to do an experimental study at all. Okay, so again, I want you to just to see the relationship between these two different kinds of studies. Now let's have a look at our experimental study and let's ask, is there any ambiguity that's possible in this study? I honestly don't think there is. I think this is a really well-designed study, right? We have recruited our women. We have given some of them vitamin D supplements. So we know that they're going to have higher levels of vitamin D intake as long as they're actually taking those supplements. We would presumably give some kind of placebo supplement to the other women. So I haven't put that in here, but that's an important part of these kinds of studies, is to make sure that there's a placebo, because you don't want the difference in testosterone to be based on people just taking something as opposed to taking nothing. And then we're going to measure testosterone and see if it's higher or lower or not different at all in those women who are taking the vitamin D supplements. So I don't think there's any ambiguity whatsoever in this experimental study. I think this is a good study design. I don't want you to come away with the impression, though, that every time you do an experimental study, there's not going to be ambiguity. So let me talk about some other experimental studies where there could be ambiguity, and you have to see that ambiguity in advance to make sure that you design a better study. So here is another research question. Do men sweat more than women when exercising? Okay, so that's a question that we've come up with. And here is an experimental study that I've designed to address this question. So I recruit 5 men and 5 women. I have them run on a treadmill at 10 kilometers an hour for 15 minutes at room temperature. So if you just look at that statement, I've done a lot of controlling there, right? I've controlled the type of exercise they're doing. I've controlled the intensity of the exercise, the duration of the exercise, even the temperature of the exercise, right? I want to make sure that the exercise is exactly the same that the men and women are doing, so that I can be assured that any difference in sweat rate that I observe is not due to, men tending to run longer or women tending to run more intensely, or, differences in temperature or something. I've controlled very precisely the conditions under which the exercise will occur. So I've removed the ambiguity that could have been present in this study if I just said, go out and run on a treadmill as you please. And then, of course, I measure their sweat rate while exercising. Okay, so there's my experimental study. Here are the results that I got. The sweat rate during exercise was 2-fold higher in men than women. Okay, so I have the answer to my question, right? No ambiguity? Wrong. Yeah, hopefully you're sitting there thinking, no, there's definitely ambiguity in this study. And the major ambiguity I can think of, at least, is, well, what if the sweat rate of men was 2-fold higher than women even while they were at rest? Let's imagine that at rest, men have a 2-fold higher sweat rate than women. And then, of course, when they exercise, ultimately now, even if they were to sweat, even if the additional sweating due to exercise were the same in both men and women, the men might still have 2-fold higher exercise sweat rates than the women. Not because of differences in how they sweat in response to exercise, but because of that initial resting rate of sweat production. So really, I would say that in my study design, I should measure the sweat rate of both men and women while they're resting at room temperature in this case, or perhaps while they're just standing on the treadmill running 0 kilometers per hour, just standing there. But I should have a resting level of sweat rate measured. And that way I'll know that if the resting rate of sweating was the same, and then men end up 2-fold higher than women after exercising, well, now I know that that difference during exercise was due to the exercise itself and not due to there being a difference in baseline sweat rate prior to exercise. Now, you might be sitting there saying to yourself, well, is this really necessary? Because you might say to yourself, like, do we actually sweat at rest? Well, I'm kind of sweating a little bit right here because it's a little bit warmer in this room than I thought. Probably don't need this sweater. You might say, well, but we kept them at room temperature, so people don't usually sweat at rest at room temperature, do they? I mean, certainly you could try to argue and use logic to say there shouldn't be a difference in sweat rate between men and women at rest because we don't expect them to be sweating at all. And therefore, the difference that we're seeing during exercise is due to differences in how they respond to exercise in terms of sweat. You could try to do that. But what I would say is people would prefer to see data than listen to you make a logical argument for something, right? So if there had been, say, previous studies where they had measured sweat rates in men and women at rest and no difference had been observed, okay, well, then you could cite that study and perhaps you don't necessarily need to repeat that work here. But unless you have a study which is going to make the case for you, you are always better off to just generate the data yourself, right? And that way your reader who's reading the paper will be convinced that yes, there's data to support the idea that resting sweat rate is the same between men and women, and therefore the twofold higher sweat rate that we observe during exercise in men is because men sweat a lot more during exercise, not because they have higher baseline sweat rates at rest. So again, don't try to use logic to talk your way out of a bad study design. Make sure that your study is designed in an unambiguous way, and then you won't have to spend so much time making an argument as to, oh, well, we didn't do this and that and the other thing, but we don't think it was really necessary and we'll try to talk our way out of it. Just design a good study to begin with, and you won't have to worry about that. Okay, I want to give you another example here of potential ambiguity in a study, an experimental study again. So my research question in this case is, do cortisol levels increase following insulin injection in type 1 diabetics? So type 1 diabetics are injecting themselves with insulin, and we just want to know whether that insulin injection has any effect on cortisol levels. Now, here's my experimental design. It says I'm going to recruit 10 patients who have type 1 diabetes. And it says here 5 male and 5 female. Now in this case, my research question did not have any element of sex to it. So if there's nothing sex specific about your question, it probably is a good idea to do your study with both males and females. There has been a long history in physiology of doing work mostly with male patients, and just assuming that the results we get with male patients would be identical to what we'd see in female patients. But we, of course, know that's not true. Male and female bodies are, even at the physiological level, very different. So if there's no sex specificity to your research question, I would strongly encourage you to work on both males and females in your study. Okay, so we've got our 10 patients. We are going to measure their plasma cortisol levels over a 4-hour period before the injection. And then we're going to inject them with insulin. And then we're going to measure them, their plasma cortisol levels, again, for the 4 hours after the injection. And this will allow us to see if insulin injection has any effect. And here are the results that we obtained. So cortisol levels were 2-fold higher after insulin injection than before. Okay, so we have the answer to our question, right? No ambiguity? Okay, hopefully you're saying, no, there's ambiguity there. One thing you might have thought is well, we didn't give cortisol injections to healthy individuals to see what happens to we didn't give insulin injections to healthy individuals, so we don't know whether cortisol levels rise in response to insulin injections in healthy individuals. Maybe that's an ambiguity in the study. The answer to that is no, it's not. Because ultimately, if you think back to what our question was specifically, does cortisol level increase following injection in type 1 diabetic patients? So our question didn't care about healthy patients whatsoever. So why would we do insulin injections in healthy patients to see what happens when they inject insulin, what happens to their cortisol? That's not helping us answer the question at all. We're not interested in comparing. The question didn't say, is there a difference in cortisol increase following insulin injection in healthy versus type 1 diabetic patients? That wasn't the question that we were interested in answering. So you have to be also careful that you don't try to add components to your study design that are irrelevant to your study design. If we had done this experiment where we also had healthy patients and shot them full of insulin to see how it affected their cortisol, I would argue that that was a completely irrelevant waste of time, because it doesn't help us to answer the question that we're asking at all. And in fact, even if we think about this from an ethics point of view, one might wonder, well, healthy patients don't normally inject insulin because they make their own. There could be ethical conundrums here with respect to injecting insulin into these healthy patients in the first place. Excuse me. So that was not the ambiguity. What I think the ambiguity was here was that we don't know, based on the experimental study design, we don't know whether the insulin injection was actually the cause of the higher cortisol levels or whether it was simply a function of time. Because how do we know that cortisol levels don't just vary naturally over the course of the day? And so they happen to have been lower during the period before the injection, and maybe they were just going to rise naturally during the period after the injection, and we just happen to give the injection in between. So the way for us to remove that ambiguity is, of course, to have a group of patients, type 1 diabetic patients, that we don't give an insulin injection to, right? We either give them no injection, or ideally, we would inject them with saline or whatever the insulin happens to be dissolved in. Now, on HumMod, as far as I can tell, you can't give a saline injection as a control. So you would probably just give no injection. But what you would do is you'd have your one group where you're giving them an insulin injection, and you measure cortisol 4 hours before and 4 hours after and see if it changes. But then you have to have a second group where you measure cortisol for that same 4-hour period before and that same 4-hour after, but there's no injection given. And this will now allow you to account for just kind of this natural fluctuation in cortisol levels that might be happening over time. If you see a rise, for example, in cortisol levels following the insulin injection, but there's no rise or a smaller rise in those who are not given any injection, now you can be confident that yes, it's actually the insulin injection itself that is causing the rise in plasma cortisol, and it's not just natural variation with respect to time. Okay? So again, what I hope you can see here is that we really have to be planning our studies through this lens of removing the ambiguity as much as possible in our study design. And the more ambiguity that we can remove from our study design, and especially if we can actually, again, do it through the design of our study and the data we will collect, rather than trying to use our logic to talk ourselves out of poor study design, the more that we can remove ambiguity from study design, the more that our readers can be confident in the data that we've collected and be confident that we've actually answered the question that we set out to answer. Now, there's one more aspect of study design that I think is important for us to talk about here, and that is the idea of justifying design choices. You'll find that when you are designing a study, there will be all kinds of choices that you have to make, and you can't just make random choices. You have to justify the choices that you have to make. So let me talk about this again in concrete terms, going back to my experimental study that I designed for this question about vitamin D intake in testosterone and in women. So we had this study where, again, we were going to recruit 10 women. We're going to give half of them vitamin D supplements. We're going to measure blood samples to assess testosterone levels and see if there's a difference between our treatment and control groups. And we said there was no ambiguity in that study design, but we do have a lot of choices that we have to make, and we have to justify those choices. So what am I talking about? Well, choice number one, when it comes to recruiting 10 women, the first obvious question is, well, what women do we recruit? I mean, there are obviously, billions of women on the face of the earth. So if we're only choosing 10 out of those billions, which ones do we choose? And I would say that your choice really comes down to two things. Do you want to work with just the general population? Okay, so you could just draw 10 random women from the general population. We have to recognize, of course, the general population and the women who are in the general population are quite variable. They vary with respect to race and age and weight and height and all kinds of other characteristics. So on HumMod, and I think this is one of the potential shortcomings of HumMod, and I wish they would kind of add on to this in the future, but you can't just go into HumMod and say, give me a random person to do my experiment on. You do have the capability, it's under the context tab, you do have the capability of changing the sex and the age and the weight and the height of your individual. So if we were doing this study with this experimental study with HumMod, and we just wanted to work then with a general population of women, what we would have to do is we'd have to open up HumMod, we'd have to go into that context tab, and we just have to kind of randomly set the age and the weight and the height of these women. So we just go in there, randomize those values, and then execute our experiment and collect our data. And then we would shut the program down or restart it, and we would go back in and just randomize a new age and height and weight and do the experiment again, and then restart and do that again 8 more times. But if you just go in and kind of randomly change the age and the weight and the height, okay, then you're ultimately going to have kind of a general population that you are working with for your study. Now, you should, of course, record the actual age and the weight and the height and whatever other characteristics you can change. I think muscularity is on there too. You should, of course, record for each of your 10 women what the starting values were for age and weight and height, because you should report that patient data also in your study. You should say that and you can do that right in the methods, but you can also do it in the results. You can say, okay, here were the characteristics of our patients. They had an average age of 35. They had an average weight of 145 pounds or something. You often want to present that patient data as part of your study, and that way people will have a sense that, okay, this is the average women that you were working with in this study. And perhaps if another similar study gets done in the future, and maybe they happen to work with slightly older or younger women than you did, then if they get different results, they might be able to say, oh, well, maybe this is because of the different age of the population that was used. So it's really important that you, if you decide to work with a general population of women, that you kind of randomize each participant on HumMod, but that you record the data about that woman. And that way you'll have those data and you can present them to tell us about your population. Of course, another way that you could approach recruiting women is that you might not want to work with the general population. You might want to work with a more specific, relevant population. So in the context of my research question here about vitamin D and testosterone in women, back in the second module, when we were talking about the relevance of that research question, one of the things we talked about is that testosterone, although we think of it as a male sex hormone, definitely has roles to play in women. It's important for things like sex drive. It's important for things like mental health and wellness. And so I might want to say to myself, maybe I should work with a more specific, relevant population. For example, if I think about the sex drive aspect of testosterone, I might say to myself, well, younger women typically engage in sexual activity more than older women do. So maybe I'll focus my study on a younger population of women. Maybe I'll recruit women who are between the ages of 20 and 40 only, and I won't recruit older women. And my justification in that case will be that, I've got this paper here that tells me that, sexual libido drops way off after 40 years old. And so I want to focus on a population of women that are still very sexually active, right? So there's a decision that I've made to narrow my study group down to a more specific, relevant population, okay? So again, you have to be thinking about the general population is a default. I think if you just decide to work with the general population, you don't necessarily have to justify that decision. But sometimes it's worthwhile to focus your research efforts on a specific, more relevant subpopulation. And in that case, you should provide not only the details about, okay, which women did we actually recruit, but also the rationale for why we didn't just recruit from the general population. The other thing, of course, you have to think about, and this is a little bit harder to do in the context of our short communication assignments, but you do have to think about, well, how many women do we recruit? I gave here the number 10, and that was kind of a random number. So that's not, choosing random numbers of people to study in your, to investigate in your study is not what scientists want to do. So the question of how many patients do you actually need in your study, well, the biggest way to answer that question is to think about what we call statistical power. Statistical power is basically the capacity to actually see a significant difference in an experimental study, or see, I guess, a significant correlation in an observational study, given the variation in the data that exists. So what I mean by that really is, statistical power basically tells us that the bigger your sample size is, the more likely you are to see a difference between, say, the supplemented and the unsupplemented women. If I recruited 1,000 women into the study as opposed to 10, I'm more likely to actually see a difference in the vitamin D effect on testosterone than if I had just recruited 10 women. However, at the same time, if the effect that vitamin D has on testosterone levels is actually a quite significant effect, then I might be able to perfectly see it with even just 5 women instead of 10. So the number of women, in this case, that I would have to recruit into my study to have adequate statistical power depends largely on how big I think the effect of vitamin D on testosterone is going to be. And again, that might be hard to do. I might look at studies in men and say, well, studies that were done in men showed a big effect of testosterone on vitamin D, and typically only used about 5 or 10 men in those studies. So I can follow suit and use about 5 or 10 men here, or 5 or 10 women here instead. Again, this is a bit hard to always know because you don't know how big the effect is going to be. So you don't want to necessarily have 1,000 women in your study because that could just be too big and unwieldy to deal with. But you also don't want to have so few women in the study that you actually can't see if there's a significant difference, a significant effect in this case of the vitamin D supplementation. So this idea of statistical power and trying to determine the sample size that's most appropriate is a tricky one. But one of the things I'll say about this is, although oftentimes we think it's ideal to determine the sample size before the study gets going, there's nothing wrong with changing the sample size during or even after the study. So in the context of your HUMOD study, for example, let's say you decided to recruit 10 women, or I decided to recruit 10 women to do this study. And at the end of the study, I can see that there is a trend where the vitamin D level seems to be a little bit higher in my testosterone. The testosterone level seems to be a little bit higher in the vitamin D supplemented group. But it's not, there's a lot of overlap perhaps in my error bars, for example. So there's a trend in the right direction, but it doesn't actually really look as though it's statistically significant. I might say, okay, well, maybe I'll recruit 10 more women. And that will help to clarify whether there is or is not a difference. So it's perfectly fine, I think, to alter your sample size even during or after the experiment has taken place to do so from that statistical power perspective. Because ultimately, we want to make sure that we're not getting false negative results in particular, right? We don't want to be getting, we don't want to be saying that, oh, vitamin D had no effect on testosterone, but it turns out that it actually did, and we just didn't see it because we had too few patients in our study. Again, this is a very tricky aspect of science, and this is the part that I think we don't have to worry too much about perhaps in the short communications per se. But if you wanted to kind of stick with 10 as a good baseline number of people to include in your study, I would generally support that decision. But you're certainly capable of making that number bigger or smaller if you can find some way to justify it, okay? The other thing, another decision that we have to make, another choice we have to make in this particular experiment is that we're going to be giving women vitamin D supplements. And so, of course, we have to think about, well, how much vitamin D should we give these women? And when you have a choice like this to make, the first thing I would say is look for precedents. So go back into the literature and say, okay, have there been any previous studies where women have been given vitamin D supplements to test for not testosterone, because that's novel, but to test for other things? And if there have been other such studies, then I can look and say, okay, well, how much vitamin D did they give? Okay, well, then I'll give the same amount. And I will cite this study to say, hey, in previous studies, and here's my reference, women were given, 10 units of vitamin D as a supplementation, and that was sufficient to show effects on, heart rate or whatever. And so here in the present study, we are going to give that same amount of vitamin D as a supplement. So that is using precedents. It's basically saying, hey, this is what other studies have done, and so we will follow suit with those other studies because this dosage of vitamin D has been established previously in the scientific literature. Now, of course, you might find that there are no such studies where vitamin D has ever been given to women. Maybe I start looking at vitamin D supplementation in men, and assuming that a similar supplement level in women would be fine. That's another way I could go. But if you can't find any good precedents, then the next thing to think about is the relevance. So in the context of vitamin D supplements, if I was to go to the store right now, the grocery store, and I was to look through the kind of natural food section of the grocery store, they've got vitamin D capsules on the shelf. And so I could imagine that if women were going to actually go and take vitamin D supplements to try and boost their testosterone levels, they would go to the grocery store, they would go to the natural food sections, they would buy this vitamin D, this jar of vitamin D capsules, and they'd say take one a day, because that's what it says to do on the container. So what I might do then is, okay, well, what's the amount of vitamin D that's typically present in one of these capsules? Oh, it turns out it's 15 units. Okay, well, then that's what we'll do for our study. So in this case, we have a relevance argument that we've made here, that this is the amount of vitamin D that is contained within these vitamin D supplement capsules that are freely available in pharmacies or grocery stores. Excuse me. And so that's the rationale for this particular choice. Okay. But what you have to really appreciate here is that either I had precedence or I had relevance that I could use to justify the vitamin D supplementation. I did not just take a dice and roll it and say, oh, a number 4 came up, I'll give them 40 units, right? Your choices cannot be random. They have to be rooted in some kind of justifiable decision making. Now, if we continue on through our experimental design, we can talk next about blood samples. So we're going to take blood samples to assess testosterone levels. A question that we have to decide with that is, when do we take these blood samples? You know, do we take them at 8 a.m. in the morning? Do we take them at 8 p.m. at night? Do we take them just before a person has eaten, just after a person has eaten? Like, when should we be taking these testosterone levels? And so again, I would say that you want to look for precedence. And then if you can't find precedence, you want to think about relevance. Okay? Now, if you can't find either of those, then you might think also about practicality. That would be the third factor you might consider here. So let's say that I went into the literature and I couldn't find any studies where women's testosterone levels had ever been measured in the past. So I have no precedents to work from. I think about relevance next, and I realize that testosterone levels in women pretty much are constant throughout the day. So they're not fluctuating. There's not periods where it's high or low. So from a relevance point of view, when I take those testosterone samples, perhaps doesn't matter. Well, then the last thing I can think about is practicality. And practicality would probably tell me, okay, well, I'll take the measurement at some point during the day because I probably don't want to have to wake these patients up in the middle of the night to get their blood sample. So maybe I take it right smack dab in the middle of the day. And practicality now is my justification for that decision. Okay? But again, in the order here is a hierarchy. It should go precedence, relevance, and then practicality when you're making these kinds of decisions. Okay? But what I hope you can see here is, again, I've got my experimental design here. I've got my experimental design, but I've justified every choice that I had to make in that design. None of my choices should be random. Okay, so that brings us then to the end of the module, where I want to just talk about what are you submitting for this module. So what you are going to submit to finish up this module is you're going to submit the methods for your first short communication. Like the introduction that you wrote at the end of module 2, your methods should be approximately 500 words. And what I want to say here is that your methods section, the methods section of a scientific paper, and therefore the methods section of your short communication, has two main objectives. And you have to do both of these in writing your methods section here for the first short communication. The first objective is to convince the reader or the reviewer, which in this case, of course, is the teaching assistant, that your study design is unambiguous and justified. Okay, now we just talked about those things. We talked about how to look for ambiguity. We talked about justifying design choices. So when you're writing the methods of your paper here, your short communication, as you are writing those methods, you want to make sure that you are conveying to the teaching assistant who's going to read and review your work that your study design is as unambiguous as possible and that you have justified any choices that you had to make with respect to study design. Okay? And so that needs to be incorporated into the methods section. The second objective of a methods is to be sufficiently clear that another scientist could repeat your experiment exactly. So the way to think about this is, if I were to take your short communication and I were to give it to one of my students next year who are taking this course and say to them, I want you to execute exactly this experiment that my students last year did and see whether you get the same results. Would they be able to read your methods section and be able to go into HumMod and execute exactly what you did? Because you have written your methods in such a clear way that it's very obvious what you did, and another person could easily replicate those steps. Okay? So that's what you're trying to accomplish here as you write the methods to your first short communication. That you make sure that your study design is unambiguous and justified, and that is clearly articulated in the writing of the methods, but also that you have written the methods in a way where another person, perhaps a future student, that perhaps is the best way to think about it, a future third-year student taking BioC32, if we gave them a copy of your methods section, could they execute that experiment exactly as you did? So that's what you want to focus on as you are writing up the methods section here for your first short communication, and this is what you're going to be submitting as your Module 3 submission. The teaching assistants, just as they did for Module 2, are going to evaluate your work. And if they approve your work, then Module 3 is complete and you can move on to Module 4. And if they reject your work, just as we did for Module 2, feedback will be provided, and you can use that feedback to revise your submission, and then you can resubmit, and you'll be reevaluated, and you just keep going through that process until you finally get your submission approved, and then you can move on to Module number 4. All right. So that's all I have to say about study design and about writing up the method section of your first short communication. So you've got your question, come up with your study design, write a clear method section, thinking about the lack of, not wanting ambiguity in your study design, wanting to justify the choices you have to make, and being clear as possible with the way that you describe your procedures, and you'll be in good shape. All right, so I will stop talking now, and I'll see you in the Module 4 video. Bye-bye.